So we've already proven that an odd number squared is always going to be odd. So we know that this statement is true. Our next maybe thing we might want to ask ourselves, well, given this, because we have an odd to the power of a specific positive integer, is it true that this kind of relationship holds for any power of a positive integer? Odd to the power of any positive even is going to also be always odd. I'm not looking at the negative evens because when I did the proof for all evens to the power of all evens, I realized that, hey, if the power is negative, it's not going to give you an integer. It's going to give you a fraction, which is neither odd or even. So we're not even going to consider that case. So we're going to ask ourselves, given this is true, the next logical question is, well, is the more general case going to be true? All right, so now that we're focusing on this question, first thing, think of some examples, right? Let's take the odd number to be 1, and let's take the positive even number to be 2, 4, and 6. Well, we know that these are all going to be equal to 1, and 1 is odd, so we know that probably an odd number like 1 to the power of any even is going to be odd. Well, let's check another number. So let's keep our powers different, but the same set. Let's try maybe 3. And I'm thinking I maybe won't do 3 to the power of 6. That's way too much of a large number to do in your head to check if this statement is maybe true. So this will just be enough. So we'll say 3 to the power of 2, that's going to be 9. 3 to the power of 4 is going to be 3, 9, 27, 81, I think. Yes, yeah. So we've already looked at some variety of odd and even numbers, so I'm thinking that this statement is likely true. So let's go ahead and try and prove it. First, let's write this out as a complete mathematical statement. What are we looking at? Any odd number to the power of any positive even number. So it's a for all statement. So we write down for all. I'm going to label our odd number A and our positive even number B. So we're going to say for all A, B that are going to be integers where A is odd and B is even, is A to the power of B odd for B greater than or equal to 2. Okay, this is going to be what we're going to actually be trying to prove, that for any integers, or sorry, for all integers A and B, where A is odd and B is even, is A to the power of B odd for B greater than or equal to 2. Why are we asking greater than or equal to 2? Well, the smallest positive even number is 2, so we're looking at least 2, and every number up to infinity greater than that, that's even. Awesome. There we go. So I've already proven that an even to the power of a positive even. So I've already got a kind of a hint of how to do this, and this is going to be done by induction, because a direct proof will be very difficult. And the way I know that it's going to be by induction is anytime one of your variables has a restriction on one end and a no restriction on the other, so in this case we have a lower boundary, we have b can't be less than 2, you're probably going to have to do a proof by induction. So let's start that proof. How do we start proving a for all statement? Well, we do with let, right? We write down let. What do we let? We let A, B be integers where A is odd and B is even, or yeah, B is even and B is greater than or equal to 2. And then we're also going to say, so A is equal to 2m. We're going to define A just because I'm going to be using A a lot more often. A is not the one with the inequality, so we know we're going to be rewriting A a few times, so this is going to save us some writing space by just defining it overall for our proof. So let's start by proving the base case. The base case in our question here is going to be when B is equal to 2. That's going to be our first domino in my analogy. If you're not sure what I'm talking about, go watch the previous video on the case where we're looking at evens to the power of positive evens. So anyways, let's look at the base case. So we're going to let B equal to 2. Then we're just going to write A to the power of B is equal to A to the power of 2, which is going to be equal to 2m to the power of 2, which is going to equal to 4m squared, which is going to equal to 2 times 2m squared. All right, fantastic. We already see that. Did I mess up somewhere? I did mess up somewhere. A should be, first of all, odd. I've defined it to be even. And the second thing is I need to also define what my m is, where m is an integer. Okay, we fixed our mistake. So we can continue our base case. Let b equal to 2. Then a to the power of b is going to be a to the power of 2, which is going to equal to, let's plug in our a, it's going to be 2m plus 1 to the power of 2. I don't see any way to write this as 2 times some huge integer or some integer in general. So we're going to probably have to expand these brackets, which is not a big deal. This is just going to be equal to 4m squared plus 4m plus 1. Now I can see how we can factor out a 2. We're going to factor out a 2 out of 4m squared and 4m. So we're going to just put a arrow here just to continue our thought process. We're going to say 2 times 2m squared plus 2m plus 1. Awesome. We've already got it to look odd. So all we have to do is just explicitly state where what's in the brackets here is just an integer, right? Where 2m squared plus 2m is an integer. So a to the power of b is odd when b is equal to 2. Cool. We've proven the base case. That works. Next, what do we have to do? We need to do our induction step. We need to prove that for every b greater than 2, that this also holds true. So let's write that down. So in our induction step, we're going to create a variable k. We're going to say let k be an integer where k is even and k is greater than 2. I'm filming this back to back with my even video, so if this is supposed to be greater than or equal to 2, I'll correct that down here, or I'll just explicitly say I'm right. And we're going to use our induction hypothesis. We're going to say, so a to the power of k is odd, so a to the power of k is going to equal to 2q plus 1 for some integer q. Okay, great. Now what do we want to prove? Well, we want to show that a to the power of k plus 2 is also odd, similar to how a to the power of just k is odd. Now, maybe we can assume the reader understands why we're saying plus 2, but the reason I'm saying plus 2 and not plus 1 is because the next even integer is always going to be plus the previous one, right? If you have 2, what's the next even integer? 4. How do you get that? 2 plus 2. What's the next even integer after 4? That's going to be 6. How do you get that? 4 plus 2. It's going to be 6. What's the next even integer after 6? It's going to be 8. How do you get 8? Well, you take the previous integer, 6, and add 2 to it. So all of these are going to be plus 2. And that's our restriction on k. K has to be even and it has to be greater than 2. So it must be that the next k has to be 2 plus the previous k. Now I'm explaining this because I'm actually going to prove this. I'm going to prove that the next consecutive, that any even number plus 2 is still going to be even. So I'm going to quickly prove that. I'm going to say, since any even number plus 2 is still even, right? I'm just trying to justify why I'm doing k plus 2 and why k plus 2 still makes our a to the power still to the power of an even integer, right? So I'm just going to do a proof within a proof real quick. I'm going to say proof, let some random integer x be an integer, where x is even, so x is equal to 2y, then x plus 2 is going to equal to 2y plus 2, which is going to equal to 2 multiplied by y plus 1, where y plus 1 is an integer. I'm not going to give too much thought, but I think this is pretty straightforward. It's almost actually identical to the even plus even proof we did, right? So this is almost a copy of that. So we can just conclude, so x plus 2 is even. Fantastic. Okay, we've justified our statement here. Now we got to do our actual induction. So what do? We try this and try and show that it can be odd, right? So let's start with what we're given. We are given that a to the power of k plus 2. Well, how can we write this? Well, knowing our power rules, this is the same as saying a to the power of k multiplied by a to the power of 2. Why did I do that? Well, remember, in our induction hypothesis, which is here, when we're doing our induction, we want to get what we suppose. So we want to get a to the power of k. Why do we want to do that? Because then we can plug this in instead, and it'll almost always make your proof way simpler. So what can we do here? We can say that a to the power of k is equal to 2q plus 1, close bracket, multiplied by a squared still. Right, because if you just, well here, I'll explain in a second. So then let's plug in our a. So our a is going to equal to, so it's going to equal to 2q plus 1 multiplied by, our a is odd. Did I say a is even somewhere? No, I didn't. Okay, I'm getting mixed up. There's so much happening in this proof. Just need to take a second to quickly look over my work. Okay, yeah, we should be fine. So a is 2m plus 1 squared. Because if we plugged, if we didn't get a to the power of k, we would have plugged the following in for this step. We would have said 2m plus 1 to the power of k multiplied by 2m plus 1 to the power of 2. And then how do you compute this? How do you multiply these together? We don't know what k is. K can be anything greater than 2. So that's why it's always good to get rid of the vague assumption we made of k. So awesome. All that's left is to basically, all that's left is to really just like expand this. If you don't want to expand this, you can maybe prove that an odd number squared is always going to be odd, and an odd times even is always even. But that's writing more proofs. I think it's just easier to expand the bracket. So let's do that down here real quick. We're going to say 2q plus 1 multiplied by 4m squared plus 4m plus 1, which is going to equal to, now we can multiply these two brackets together. It's going to equal to 8qm squared, right? This times that. Then we can say plus 8qm plus 2q, okay. Then we take our 1, which is going to be plus 4m squared plus 4m plus 1. Okay, fantastic. We have all of these that could be multiples of 2 plus a 1, so we're already looking good, like we're going to get something equal, odd. So all we got to do now is factor out a 2 out of what I've underlined here. So we're going to write another arrow. We're going to say 2 multiplied by 4qm squared plus 4qm plus q plus 2, right? Yeah, plus 2m squared plus 2m, close bracket, plus 1. Let me just erase this. Okay, a lot of pre-calculus here. Fantastic. And now we have to make our final argument where 4qm squared plus 4qm plus q plus 2m squared plus 2m, that's a mouthful. All of this is an integer, so a to the power of k plus 2 is odd. I'm going to save space. You can of course say so a to the power of k plus 2 is equal to this equation here, so a to the power of k plus 2 is odd. But that's going to take up a lot of space. This is already a lot of writing. We should be fine now. Yeah, so we've shown both in the base case a to the power of b is odd, and in the induction step, any following b is going to also be leading to this being odd. And then you just write your conclusion. You would say, in conclusion, via the base case and induction step, demonstrating that the statement is true, the statement must be true. So, awesome, that's just the detail. But we've proven the statement.